Welcome back to Maths with Mrs. J. We've been talking about complex numbers, and in particular we've been talking about complex numbers when they've been in Cartesian form, so where there's a real part and an imaginary part. We've talked about what they would look like in the complex plane. The other way of determining the position of a complex number is in polar form. Now, sometimes you will see an Argand diagram, which is a bit like this, but with concentric circles with centre at the origin. And that's talking about how far, it's a bit like a unit circle with trigonometry, but with different sized circles in this case, because your R here can be bigger than 1. Your theta, the angle, is always going to be measured anti-clockwise from the positive direction of the real axis. Just like with our unit circle, it's always measured anti-clockwise from the positive direction of the x-axis. If you're going this way, it's counted as a negative angle. Now, let's have a bit of a look at this and see how we would use this information and our trigonometry information that we know. Yes, we are going to have to use our trigonometry information to convert from Cartesian form to polar form. Okay, alrighty. Just a little bit of terminology for starters. The absolute value of Z, otherwise known as the magnitude or the modulus. Sometimes, in fact, often we use R instead of having to write that. We're a little bit lazy as mathematicians. That's the distance that your complex number is from the origin. Your theta must be in radians, and that's your angle or your argument. Okay, let's have a look at this right-angled triangle. How are we going to work out R? Well, R's quite easy because we've got a right-angled triangle and we know Pythagoras. So R squared equals A squared plus B squared because of good old Pythagoras. So R is going to be, it's perfectly okay to just take the positive square root there because we're talking about a length, okay? Now your theta, let's think about your theta. Tan of theta is your B on your A. So theta is inverse tan of B on A. But, there's a very big but here, but you can't just use your calculator here because remember, tan is positive in the first and third quadrants. If you do inverse tan, even if your calculator's in radians, if you do inverse tan of a positive, it will only give you the first quadrant answer. What if your complex number's over here? And also, if you're doing inverse tan of a negative number, it's only going to give you your second quadrant, whereas tan is negative in both second and fourth quadrants. So how could we put this? Draw a diagram to ensure correct quadrant. All right, we should always have a little sketch just to make sure that we're doing the correct thing. Now, how we want to put our complex number in our polar form is we want to be able to write it, we want to be able to write Z as R cis theta. What on earth is cis? Well, cis is cos theta plus I sine theta. We're very lazy in maths. We like having little shorthand ways of doing things. So the real part is R cos theta, and the imaginary part is R sine theta, isn't it? So let's just do this. So our real part is our A, and that's our r cos theta. And our imaginary part is our b, and that's r sine theta. Okay, and that's how we go from there. We can, in fact, if we want to, well, we know anyway that cos of theta is a on r and sine of theta is b on r, so that helps us work that out anyway. Let's move on and actually do some examples. I'm only going to do 2 examples because I want to actually go into detail about where they are on the diagram and how you get the angle and all that sort of thing. I hate to tell you this, but you're also going to have to remember your exact values from your trigonometry. Go back to the unit circle series of videos if you need to. Okay, let's move on and actually do some examples. Okay, as I said, I've only got 2 here because I want to actually take them in detail. First thing I would recommend is drawing a little diagram in each case just to show where that is. Okay, doesn't have to be fancy. In fact, it really doesn't have to be fancy at all. We don't want to waste time. So the real component here is 1 and the imaginary part is √3. All right, so that's your imaginary part and your real axis there, imaginary axis there. Okay, so here's our Z. Now, in order to write it in polar form, we need to know what is this length here and what is this angle here. Okay, let's just think about that for a minute. Well, what's the length going to be? The length is actually quite easy to work out. So we know that the length or the magnitude is going to, or the modulus, whatever you want to call it, is going to be the square root of a squared plus b squared. Because here's our a and here's our b. All right, we've got our little triangle here. Here's our A, here's our B, and here's our R, and here's our theta. Okay, so A squared is 1 squared, B squared is √3 squared, which of course is 3. So we're going to get the square root of 1 plus 3, which is the square root of 4, which is 2. So we've got a nice, easy value for R. Now, how are we going to get our theta? We're quite fortunate in that we're in the first quadrant. And what we've actually got here is this length is 1 and this length is √3. And we want to know what's theta. So we know that we're in the first quadrant. We know that for sure. And we know that tan of theta is √3. Thinking back to our exact values, what angle has a tan of √3? Pi on 3 is correct. So theta is pi on 3 in that first quadrant. So basically our Z is 2 cis pi on 3. You can just leave it like that if you like. Or you can write it as 2 cos pi on 3 plus I sine pi on 3. Okay. Let's have a look at the next one. And let's again do just a little sketch just so we can sort of see what we're doing, where we are, that sort of thing. Okay, so we've got our real axis and our imaginary axis. In this case, we've got 2 minus 2i. So we're down here for our Z. So again, thinking about what we're wanting to know what is the length of this line. So what is the magnitude or the modulus? And we're also wanting to know what is this angle. Either we could do it as a negative angle going back that way, or we could do a positive angle going all the way around. A negative angle is perfectly fine, okay? So let's have a look at this triangle that we're dealing with, just so that we can sort of see what we're doing. So we're in the fourth quadrant. We need to remember that. And we've got our triangle here that's 2 and 2. And we've got our theta here. And this is our r. Okay, well, r is going to be the square root of a squared plus b squared, which is going to be the square root of 2 squared plus, well, negative 2 squared is the same as 2 squared, but you can put it in brackets there if you like. So we're going to get the square root of 8, just simplifying that, that's 2 root 2. Now we know that tan of theta is our b on a. We know that. That's from our rules and how we work it all out. So we're going to get negative 2 on 2, which is negative 1. So this makes sense in terms of where we are. Tan is negative in that fourth quadrant. Now what we need to do is we need to think about our exact values. When is tan of theta 1 in your first quadrant? What angle would be correct for your first quadrant having a tan of 1? Yep, pi on 4 is correct. So we're in our fourth quadrant. We could just say negative pi on 4, and that's perfectly okay. So we could say z is 2 root 2 cis negative pi on 4. That's perfectly okay. If you want to refer to it as a positive angle or positive argument, what you could do is work out what 2 pi minus pi on 4 is. It's like 2 minus a quarter is 1 3/4, which is 7 quarters. So you could refer to it as that instead if you like. Same thing. Okay, now next video we're going to go back the other way, which is actually easier. You'll be pleased to know.